Hi everyone, my name is Lydia. I'm a PhD student at Northeastern University, and with Thomas Steinke from IBM Research, we propose this open problem on the information complexity of VC learning. The information complexity is a property of a learning algorithm A, which takes NIID samples from the population as its input and outputs a hypothesis in the space W. It essentially asks how much information does the output of the learner reveal about its input. It's closely related to privacy, and it's usually measured with respect to the mutual information between the input and the output of the algorithm. Another reason we care about the information complexity is that low information complexity implies generalization. And in particular, mutual information at most D implies expected generalization error at most square root D over N. On the other hand, uniform convergence is a property of the hypothesis class W. It essentially says that for any low complexity class, all hypotheses in the class generalize well. And the way we measure the complexity of the class is through some combinatorial quantities such as the VC dimension. And so more formally, VC dimension at most D implies that for any hypothesis in the class, the expected generalization error, which is the difference between the empirical and the true loss, is at most square root D over N. So algorithms that are empirical risk minimizers, that is, they return the hypothesis with the minimum loss on the data set, are guaranteed to have true loss at most, the minimum loss plus this square root D over N factor. So although we know that any learner for a VC class would generalize well, we also want learners with low information complexity because of their other desirable properties. So a natural question to ask would be, do all VC classes admit a learner with low information complexity? And the answer is no, if we measure information complexity with respect to the mutual information. Recent work showed that for the VC class of threshold functions on an unbounded domain, any proper and consistent learner must have unbounded mutual information for some bad distribution. But the answer is yes, if we measure the information complexity of an algorithm with respect to CMI. CMI is a new notion recently proposed, and it has the same connections to privacy and generalization. So we proved that any class W with VC dimension D has an empirical risk minimization algorithm with CMI at most D log n. And again, bounds on CMI imply generalization, so this bound would imply the same generalization guarantees that we saw earlier of square root D over N, which we know are true for any learner for that class by uniform convergence, except for this log n factor here. So we ask, can we remove this superfluous log factor? And we conjecture that for every class W of VC dimension D, there exists an algorithm with CMI in the order of D, which has empirical loss at most the minimum empirical loss plus square root D over N. And through the generalization properties of CMI, this would imply the desired bound on the true loss. As a reminder, uniform convergence says that for this class, the empirical risk minimizer, so the algorithm that returns the hypothesis with exactly the minimum empirical loss on the data set, has true loss of the same order. So essentially, in our conjecture, we relax to an approximate empirical risk minimizer, allowing the same empirical error of square root D over N, which is the same as the generalization bound, in exchange for CMI on the order of D. So now moving from the agnostic setting to the realizable setting, we conjecture that for every class of VC dimension D, there exists an empirical risk minimization algorithm with CMI at most D. And as evidence that this is true, we have proved that the VC class of threshold functions on the real line, which is a class with VC dimension 1, admits an ERM with constant CMI instead of log n as the general theorem would imply. We thank you for watching the video, and we hope you found this problem intriguing.